Hello, everybody. Welcome to another episode of Cosmos from Your Couch. My name is Michael Reed, and I'm the Public Outreach Coordinator for the Dunlap Institute for Astronomy and Astrophysics at the University of Toronto in Canada. And for those of you who are joining us for the first time, Cosmos from Your Couch is our series where we try and provide some interesting and stimulating astronomy content for you while much of the world is in these rotating lockdowns. So we're very grateful to you for joining us tonight for our talk about misconceptions about the universe. Just to give you a sense of how this is going to go, our guest tonight is Dr. John Percy. He's going to give his talk and then he'll entertain some questions at the end. So if you have questions, please feel free to post them in the chat at any time. We'll gather them up and pass them along to Dr. Percy at the end. So by way of introduction, Dr. Percy, who got his PhD at the University of Toronto in 1968, is now a very active professor emeritus at U of T, where he works both in astronomy and in science education. He was a founding member of the University of Toronto's Mississauga campus in 1967. His research deals with the nature and evolution of stars, and he's published over 250 research papers, which is quite a lot, and 3 books in these fields, including Understanding Variable Stars, which came out from Cambridge in 2007. He's been very active in science education, especially astronomy education at all levels throughout the world. He's edited 5 major conference proceedings in the astronomy education field, has served as president of 6 national or international scientific and education organizations, and as vice chair of the board of trustees of the Ontario Science Centre, as honorary president of the Science Teachers Association of Ontario. He's also received many awards, including most recently the inaugural University of Toronto President's Teaching Award, which is the biggest teaching award at the University of Toronto, and the inaugural Keelak Award of the Canadian Astronomical Society, which is the professional body of astronomers in Canada, for outstanding contributions to the public appreciation and understanding of astronomy. He also won the 2013 Education Prize of the American Astronomical Society. He's a fellow of the American Association for the Advancement of Science and the Royal Astronomical Society of Canada. So all of that is to say that Dr. Percy is a very, very prestigious astronomer with a very long pedigree in teaching people and guiding teachers to teach others about astronomy, which makes him more than eminently qualified to give tonight's talk about common misconceptions about the universe from everyday life to the Big Bang. So I'm very happy to turn it over to my colleague, Dr. John Percy. Take it away, John.
Okay, thank you very much, Mike. Yeah, I'm sitting here resting on my laurels. But anyway, welcome to tonight's barrel load of misinformation. That's basically what we're going to do here. And I'm going to lead you through it. And in a way, it's going to be a kind of backward introduction to astronomy through all these misconceptions from everyday life to black holes to the Big Bang. But as well as highlighting these, what I want to do is to encourage you to actually go out and make some observations of the sky, to do some simple demonstrations, and to do some critical thinking. Because one thing about misconceptions is that they're really, really resistant to change. So first of all, what is an astronomical misconception? It's not just something that we don't know. It's something that people are sure that they know about the universe, except that it's incorrect. And there's a whole bunch of different kinds and causes of these misconceptions. And I'm going to try and highlight these because you'll realize that, that these misconceptions or other misconceptions can arise in just about any field, anything in your everyday life. So it's really important to understand where misconceptions actually come from. So I want to start with misconceptions about astronomers. If you look at the left-hand cartoon here, here's your stereotypical graying white male gazing up at the sky. And on the right-hand side, another stereotypical graying white male with a funny hat gazing through a spyglass. But that's not really what astronomy is or what astronomers do. So I'd like to introduce you to a bunch of my colleagues in the Dunlap Institute a couple of years ago. And here they are. They're not all graying white males. They don't use spyglasses. They use some of the most powerful and sophisticated telescopes in the world. Okay, so let us begin with the granddaddy of all astronomical misconceptions, something that those of you in the Northern Hemisphere might be wondering about right now, and that is, why is it so darn hot in the summer? So here's a kind of a multiple choice way of approaching it, and I've given this little test to lots of different groups over the years, teachers, students, general public, and so forth. So what is it that causes a seasonal increase in temperature in the summer? I won't embarrass you by actually having you tell me what you think, but let me point out that the vast majority of people are going to choose the first one here. It's because the Earth is closer to the sun. Obviously, closer is warmer. Well, that's not the answer. The answer is that in the summer, the sun is higher in the sky, it shines more directly downward, and equally important, the days are longer. Now, one interesting thing is that if you tell people that the first answer is not correct, then a lot of them will gravitate towards the third one, because they've heard something about the tilt of the Earth's axis. So they figure maybe, well, if the Northern Hemisphere is tilted towards the sun, it's going to be a bit closer. And that would work if the Earth were really close to the sun. But the fact is that the Earth's distance from the sun is about 10,000 times its diameter. So actually, this is completely trivial. The reason is number two here. Here's a schematic view of how the sun moves during the summer, high in the sky, 16 hours above the horizon, whereas in the winter, it's only above the horizon for maybe 8 hours, and it's never very high up in the southern sky. So why this misconception here? Well, here's a diagram from a science textbook. Now, the diagram is actually meant to illustrate the fact that the Earth's orbit around the sun is not exactly circular. It's non-circular by about 1%. And what they've done here is to exaggerate it. And obviously here, it looks like the Earth is much closer to the sun where it is right now, and will be much further away 6 months from now. So that's not helpful at all. But again, the simplest, most common explanation is simply that, well, nearer must mean warmer. Here's another one, a very common one that all of you can observe during the month, and that is the phases of the moon. So why does the moon show phases? Well, one of the popular answers is that it's due to the Earth's shadow. The moon moves into the Earth's shadow during the month. No, it doesn't. The explanation for this is that as the moon goes around the Earth, then the relative position of the sun, the moon, and the Earth is such that the sun illuminates the moon in different ways. The best way of demonstrating that, particularly if you're a teacher, is do something like on the top picture here, give the kids some styrofoam balls to represent the moon, have a lamp to be representing the sun, and you, of course, are the observer on the Earth. And so, for instance, at full moon, when the moon is opposite the sun in the sky, the sun is shining on the near side of the moon, so we see it like that. But at new moon, the moon is between us and the sun, so the sun's shining on the backside of the moon, so we're not actually observing it. So this is what causes it. And again, it can be problematic as to what causes this. So again, here's a textbook diagram trying to explain the causes of the phases of the moon. And this has all sorts of problems. First of all, it isn't to scale. Secondly, they don't tell you that you're looking at the moon's orbit at an angle. So instead of looking round, it looks oval. The big problem is that the moons around the outside are as you would see them from the Earth, whereas the moons on the inside here are as you would see them from some distance away. In fact, some people may even think that there are 8 moons going around the Earth and that they go on a track, like a streetcar track or something like that. So diagrams can be really misleading. Well, what does happen if the moon goes into the Earth's shadow? Well, we get an eclipse of the moon. This is one of a few years ago. It takes place over a course of a few hours. And you will notice that the Earth's shadow here is rounded. And that, in fact, was one way the Greeks knew that the Earth was round and not some other shape. So this is an eclipse of the moon. Okay, here's a trick question. What color is the moon? Is it white or is it black? Well, obviously, everybody knows it must be white, but no, in a sense, the moon is as black as tar or coal. It reflects only about 5% of all the light that falls on it and absorbs the other 95%. But of course, if you see a full moon against a blank sky, it certainly looks as if it's a bright white. But the fact is that if the moon were made of ice or snow, it would be about 10 times brighter because obviously ice and snow are much more reflective, much more so than tar is. Here's another question. You've all seen the full moon. You've all seen a quarter moon, first or last quarter. So how much brighter is the full moon than the quarter moon, or the half moon, if you want to call it that? Well, the obvious answer would seem to be twice as bright. Seems to have twice the area there. But in fact, it's 13 times brighter than the half moon. So why is the full moon 13 times brighter than the half moon? Well, it's because, as you'll see on the bottom left-hand picture here, that when the sun is shining on the moon from the side, then there's all sorts of shadowing, which shows up on this picture here. Shadowing by the craters, by the mountains, by the valleys, and so forth. And there's enough shadowing on the half moon there to make it much less bright than it would otherwise be. Now, here's a really neat question, and this can actually drum up a lot of dispute if you do this as a demonstration in a classroom. That is, does the moon rotate? Well, one thing that I'd like you to try and observe, if you haven't observed it already, is that as the moon goes through its phases, it always keeps the same face towards the Earth. It's always that stereotypical man in the moon or person in the moon. So does this mean then that the moon does not rotate? Well, actually not. The moon is rotating, but it's rotating in the same period of time as it goes around the Earth. Now, one way you can demonstrate this is if you take a balloon or some other spherical object and you paint a face on it, and then you take this and you move it around your head like the moon going around the Earth, always keeping the face towards the Earth. Now, yes, you will always see the same face towards you, but let your friend stand somewhere else in the room and ask them whether, as the moon goes around the Earth, do they see all the different sides of the moon, the front side, the back side, and the two sides? And they'll tell you, yes, they see all the different sides of the moon as the moon goes around the Earth. So the moon is, in fact, rotating, but it's rotating once a month, which is the same period as it goes around the Earth. Now, the neat thing is that this is because the tidal forces of the Earth have actually slowed down the rotation of the moon over billions of years until one side of it is locked towards the Earth. And very, very slowly, the moon is doing the same thing to the Earth, slowing down its rotation just a tiny, tiny bit until trillions of years from now, the Earth will keep the same face towards the moon. Here's another thing having to do with the moon. You've probably heard about the dark side of the moon. Sounds really conspiratorial. It's actually the title of a very famous album by the rock group Pink Floyd, which is where a lot of people have heard this. But is there a dark side of the moon? And is it the far side of the moon, the side that's hidden? The answer is no. So look again at this set of pictures here of the moon as it goes through its phases. And in the top row there, near new moon, The dark side of the moon is actually the side that's facing us. The reason we see it this way is because the sun is shining on the back side of the moon and the near side is dark. Halfway down these pictures here at full moon, then the dark side of the moon is the back side because the sun's shining on the front side and it's not shining on the back side. So yeah, the moon does have a dark side, but it's not always the same side, and it's certainly not always the far side of the moon. So no conspiracies here. Here's a misconception. This is something that teachers really need to know, and that is that you can actually observe the moon during the daytime. And that's important for students because it gives them some astronomy to do during class time. So they can see the first quarter moon during the afternoon. They can see the last quarter moon during the morning. And by the way, there's a famous saying of, it was George Gamow, the physicist and popularizer, who said, which is more useful, the sun or the moon? Moon, obviously, because it gives us light at night when it's dark. The sun gives us light in the daytime when it's light anyway. Haha. Anyway, so speaking of moons, the media have zeroed in on this term supermoon, which describes the moon when it's at the near point in its orbit. It's about 10% closer to the Earth because the moon's orbit isn't quite round, as compared with when it's further away, 10% further away. So when it's closer, it's about 10% bigger and a bit brighter than it would be if it was further away. The question is this significant? The answer is, if I were to show you a picture of the supermoon and then show you a picture of the moon when it was further away, you wouldn't really notice the difference. You'd only notice the difference if I showed you the two pictures side by side. But it's something that the supermoon, the media, and in this particular poster here, some new age organization has settled on, and it actually works. Here's a picture of an event that the Dunlap Institute organized a few years ago to watch an eclipse of the supermoon. You'll notice that the sky is actually cloudy, so you've got thousands of people who came out expecting something great. And they did, in fact, get something pretty good, too. I think everybody went home happy because there were lots of astronomers to talk to and lots of other fun things to do. Here's a misconception that's actually based on something quite different. It's a misconception that the moon is actually larger when it's near the horizon. But it actually just looks larger. It's the same size. This is a very famous optical illusion. But again, it's something that you can test. If you go outside when the moon is rising, the full moon is rising, you take an aspirin and you hold it at arm's length, it will exactly cover the rising full moon. And then you can do the same thing a few hours later when the moon is high in the sky. It doesn't look as big, but the aspirin will still fit nicely over the disk of the moon, showing that the size isn't really different. And if you don't believe in optical illusions, look at this picture here and tell me which of the blue circles is the larger one. Yeah, they're exactly the same. Speaking of the moon, there's also a widespread misconception that there's more crime and madness at full moon. Well, there's no evidence for this, but there is actually an explanation for why people seem to think this, and it's what you could call positivity bias. That is, if there's a crime going on and the moon is full and it's visible, you may actually see the full moon and take note of that. But if you see the same crime going on and the moon is not visible, then you don't notice it and you don't note it. Now, that isn't terribly important, but you get a similar effect in medical research publications. If somebody observes a positive effect of something on a disease, then that will usually get published, picked up by the media and so forth. But there's important studies where researchers show that something or other does not have a positive effect on some disease, or it has no effect at all. And often that's important to know. but it rarely gets published, and it certainly rarely gets picked up by the media. So it's something that you have to watch out for. It's a kind of a bias. Here's another famous misconception, and that is, why do astronauts feel weightless? You've all seen videos of them drifting around in the space station and so forth. Well, the usual explanation is that there's no gravity in space. Well, if there's no gravity in space, what is it that's causing the space station to orbit around the Earth? Because yes, there's almost as much gravity up there as there is down here, and it's pulling on the space station, it's pulling on the astronaut, but at the same rate. And in fact, if the space station was not going sideways at 10,000 kilometers an hour, then the space station and the astronaut would fall down towards the Earth and eventually crash. So you could, in fact, be weightless if you wanted by jumping off the top of the CN Tower. You'd be weightless for half a minute or so, but that's only because you don't have something pushing up on your feet. That's essentially what weight is. It's the force of the floor upwards on your feet. And in the space station, you don't have that particular situation. But you'd be surprised how many people think that there isn't any gravity in space. And likewise, there are people who think there's no gravity on the moon. There's certainly less than there is on the Earth. But that leads us to yet another misconception, and something that's really important, because this is a very good example of a conspiracy theory. About a sixth of Americans believe that the Apollo moon landings never happened. They were filmed in some movie lot somewhere or other. But the question is, what is the evidence that they give? Well, here you'll notice the sky is black. There's no air on the moon, so they would say, oh, well, there can't be any wind either. So why then is the US flag flying like this if there's no wind? Well, the answer is very simple, and that is that right across the top there, there's a curtain rod. The curtain rod is conveniently holding the flag up so that everybody can see who it was that spent $100 billion to send humans to the moon. But of course, conspiracy theories are still with us in many other areas of everyday life. Here's a misconception, and that is that the planets are actually very close to each other and maybe even are in a straight line. So here's a diagram, actually comes from NASA here, of the 8 planets. There are 8 now, not 9. Pluto got demoted. And you'll notice that they look as if they're awfully close together. Well, a good way of dealing with this is actually to make a scale model of the solar system in your schoolyard or in your community. And at least one community in downtown Toronto has done exactly this. Make a scale model in which the sun is a beach ball, for instance. And if it is, then the planets would be tiny objects spread out 1 or 2 kilometers in different directions. So the solar system is really, really spaced out. Here's another misconception, and that is that somehow the asteroid belt, this belt of small objects in the solar system between Mars and Jupiter, is really densely packed. And you may be familiar with Saturday morning cartoons in which your intrepid hero goes off on a space flight, dodging asteroids right and left. But it really isn't that way at all. I'm very fortunate to have an asteroid named after me, and if I was standing on my asteroid, I'd look out in all directions and I would see no other asteroids as far as I could possibly see. They're spread out to that extent. So a spacecraft can go from Earth out past Mars to Jupiter, and the chances of it running into an asteroid are absolutely minuscule. In fact, here's a really interesting picture. I won't tell you what reputable publisher this particular picture comes from, but there's your planets all crowded together. There's the asteroids all marching along like soldiers between Mars and Jupiter. Planets are going around on those rails, like streetcar rails there. There's a comet in the middle of things, and then just outside the solar system on the upper right, you will see the stars and even a nearby galaxy. So how could you get a worse idea as to the layout of the solar system than by looking at a diagram like this? So here's another kind of semi-conspiracy theory, and it was particularly before Pluto got demoted to dwarf planet, when it was the 9th planet, and any additional planet in the solar system would be the 10th planet or planet X. Of course, X immediately conjures up conspiracy theories and so forth. There's an unseen planet, it's being hidden by NASA behind the sun or something like that. Well, the reason that Pluto was demoted was in part because it was very small, but it was also because other largish objects were being discovered out beyond Pluto. And on this picture here, there's 2 of those, Quaoar and Sedna, which are shown, and as you can see, they're in the same size class as Pluto. So either these had to be called the 10th, 11th, 12th planet or whatever, or there had to be a new definition of planet, and that's the way it was. But there's always some suspicion of other planets in the solar system, and there's even one now that's being carefully investigated by astronomers. It seems very unlikely, and it's not a big planet or anything like that. But astronomers are always looking to see what's out there, because there are lots of things out there beyond Neptune. Okay, here's something that's topical. You may know that there was a bright comet visible in the sky last month here. And if I show this picture to the average audience, most people know that this is a comet. But the question is, what's it doing? And the misconception is that it's streaking across the sky with its tail behind it. So that's the question. Do they streak across the sky, and do their tails trail behind them like my cats? No. Here's the path of comet Neowise from last month here. And you'll notice on this map here that it goes from July the 15th to July 31st. It took 2 weeks to move a distance equivalent to twice the length of the Big Dipper. And furthermore, you'll notice that the tail of the comet is actually pointing away. It's pointing in front of the comet here. It's pointing in the direction that the comet is going. So it's like a searchlight or headlight out in front. So the tail doesn't always point backwards the way that the comet is coming from. The tail always points away from the sun. So if the comet is going away from the sun, the tail goes out in front, which leads to the question, well, why do we call it a tail if it's not always on the back end of the comet? A good example of how the words that we use, like weightless and so forth, can conjure up misconceptions. Here's something that does streak across the sky. It's a meteor, but colloquially called a shooting star or falling star. And a few people will think that, well, maybe shooting stars really are stars, things encountering our atmosphere, burning up in our atmosphere in a second or two as they pass through. Well, I would hope that a star would not pass through our atmosphere, because a star is roughly 1 million times bigger than the Earth, and obviously we don't want that. But no, meteors are just tiny bits of space dust or space rock that encounter the Earth. They're certainly not stars. Well, speaking of stars, there's a misconception that the stars are just outside our solar system, as they appeared to be on that diagram that I showed you a few slides ago. Well, the nearest star to the sun is Proxima Centauri. This is an artist's conception on the left here of Proxima Centauri, which is the thing on the left. The thing that is in the foreground is its Earth-like planet. The nearest star to the sun actually has an Earth-like planet. But the distance to Proxima Centauri is actually about 10,000 times further away than Neptune, the outermost planet in our solar system. So going back to that scale model that we did, if the sun was a beach ball and our solar system is a few kilometers at most in size, the next nearest star on that scale model would be in New Zealand. So that's why interstellar travel is not something that's likely to happen in our lifetime. Well, the stars are very far away, and that's the reason that astronomers use telescopes, not to magnify the star, because a star is a point of light, and if you magnify it, it's still so far away that it will still just look like a point of light. A telescope is to gather light, the faint light from distant objects. We call that the light gathering power, and to bring it to a sharp focus, which we call the resolving power, so we can study it with our various instruments. So we don't buy telescopes on the basis of their magnification. We rate our telescope on the basis of its light gathering power and its resolving power. Okay, so as far as stars are concerned, you may think that all stars are white. Indeed, all stars look as if they're white, but on this picture here of the constellation Orion, you'll notice that the upper left star, Betelgeuse, is definitely reddish, and the lower right star, which is Rigel, is definitely bluish. Now, stars are reddish if they're cooler, and they're bluish if they're hotter. So it's exactly the opposite to the taps in your bathroom. The problem is that our eyes are such that if we look at faint objects, then we have virtually no color sensitivity, and indeed everything does look white. You can test that by going out to the parking lot at night, and you'll notice that the cars are always the same grayish sort of color, unless they're very clearly under a light. So one useful thing you can do with constellations is use binoculars, because then the brightness of the stars is greater and your color sensitivity will kick in, and you'll get a better view of the constellation than just using your unaided eye. So what's the brightest star in the night sky? If I ask this question of most audiences, then the majority of people probably won't know the answer, but they happen to know that the name of one star, and that's the North Star. So they kind of assume that Polaris is the brightest star in the night sky, whereas in fact, it's actually number 47. Sirius is the brightest star in the night sky. You can certainly say, though, that Polaris is the most useful star in the night sky, because if you find Polaris, and I think every Girl Guide and Boy Scout learns this method that's shown on the left-hand picture here. You use the N2 stars on the Big Dipper to point to the star Polaris, and Polaris is almost exactly due north. Its angle above the north point, the northern horizon, is also almost exactly equal to your latitude. So you can actually use it for navigation, knowing where you are on the surface of the Earth. You may have learned in school that the sun is an average star. You may have been a little bit disappointed. It turns out that the sun is not an average star. It's actually bigger and brighter than over 90% of all of the stars in our galaxy. The average star in our galaxy is something called a red dwarf. This artist's conception here is what it would look like if you were standing on the Earth looking at the sun, if the sun was indeed an average star, a red dwarf, which is much fainter and much cooler and much less massive than the sun is. One neat thing is that whereas in searching for planets around other stars, we started out looking at stars like the sun, which were above average, and very soon realized that, well, maybe we should be looking at these 90% of stars that are red dwarfs. And indeed, hundreds and hundreds of planets are being found around red dwarfs, of which one example is Proxima Centauri that I showed you just a few slides ago. And it not only has a planet around it, but it has an Earth-like planet, which would have temperatures that would be suitable for life. Now, the sun is normal in the sense that it derives its energy by nuclear fusion. There's a tendency for people to think that the sun burns by coal or oil or gas or some other chemical process. Astronomers don't help matters because we refer to the sun's energy generation as being hydrogen burning, but we mean burning in a nuclear sense, not burning in a chemical sense. So the sun emits light, it emits heat. Does it emit deadly rays during an eclipse of the sun? Because sometimes people are told not to look at, well, people are always told not to look at the sun during a total eclipse of the sun. Some school principals will ask the students to hide under their desks during the totality of the eclipse, somehow thinking that the sun is emitting some strange radiation. Well, the only thing about the sun in eclipse is that it gives us a reason to look at the sun, which is something that you should never do, because if you look at the sun, at least when the bright surface is exposed, then you run the risk of burning your retina or doing other damage to your eye. So the answer is don't ever look at the sun, particularly during an eclipse, but it's not because there's some strange, deadly radiation. Well, that brings us to black holes. Nowadays, black holes are so much part of popular culture that I think most people know that a black hole is something whose gravity is so strong that not even light can escape from it. Well, here's a picture of a black hole. That's an artist's conception there. And it's actually in orbit around a normal star. This was the first black hole that was discovered. This black hole would have been the end product of a very rare, very massive star. The neat thing is that this was actually co-discovered at the Dunlap Observatory in Richmond Hill, Ontario, by my colleague Tom Bolton. So the black hole is actually taking up some gases from its companion here. But even over the course of the lifetime of the companion, it will only absorb a tiny, tiny fraction of all that gas. And it certainly won't be going around our galaxy eating up every star in sight. Black holes are not cosmic vacuum cleaners. They are nothing for us to worry about. They are just very, very interesting objects. Okay, related to that is the misconception that at the end of the sun's life, the sun will explode and its corpse will turn into a black hole. Now, it turned out that the first version of Trivial Pursuit said that this was the case. That is being corrected by now. But no, the sun's eventual fate is that it will swell up, the outer layers will drift off into space, as we see in this object here called the Ring Nebula. Those outer layers will drift off into space and those gases will merge with other interstellar gases to form a new generation of stars. And the actual corpse of the star is that tiny little point of light there, which is called a white dwarf. So this is how the sun will actually end its life. Just a couple of weeks ago, I was reading one of the newspaper columnists and they were talking about when the sun will go supernova. And the answer is no, the sun will not go supernova, nor will it turn into a black hole. Now, here's another example of language. You might think that light year is a unit of time, light year. That's what you would think. But no, a light year is the unit of distance. It's the distance that light travels in a year, traveling at 300,000 kilometers a second, and that works out to about 10 million kilometers. That turns out to be very useful astronomically because you'll notice in the picture on the left here, this galaxy of hundreds of billions of stars, which is very much like our galaxy, is 100,000 light years across. That is, it takes light from a star at one side of it, 100,000 years, to go across to the other side. Our sun is off to the left there in the suburbs of the galaxy, and it means that the light from the center of the galaxy, which is about 25,000 light years away, takes about 25,000 years to get from there to our eyes. and therefore we see it as it was 25,000 years ago. So astronomers can actually look back in time. But again, this comes from the words that we use and the fact that light year is a term that's now very popular in popular culture. Now, speaking of galaxies, this is again a picture of a galaxy much like our own. But people might look at this and assume, well, maybe this is the universe. 100 or more years ago, astronomers looked at these objects and they actually thought that they might be solar systems in the process of formation. But no, they are other galaxies like our Milky Way with hundreds of billions of stars in them. Well, that brings us to the Big Bang. Now, the Big Bang is another term which is now part of popular culture because of the TV program here. It's actually a name for the birth process of the universe. It was actually made up by Sir Fred Hoyle as a derogatory term because he didn't believe this theory here. But a lot of people will envision this, much like it's shown on this picture here, as some kind of explosion in pre-existing empty space in the middle of nowhere. But actually, the Big Bang was actually the origin not just of matter, but of space and time as we know it. And space and matter are expanding together, carrying the matter with it. And a very good analogy, which you can do in the classroom, is just take a balloon and mark some galaxies on it, like we see on the left here, and inflate the balloon. And you'll notice that as the balloon inflates, the galaxies are still fixed in space. They're not rushing in any one direction, but they are actually all moving away from each other as space expands. This was one of the beautiful ideas from Einstein's general theory of relativity. This is a slightly complicated analogy to use because it's actually the surface of the balloon that's intended to be a two-dimensional analogy for space. Because when you look at the balloon, it does in fact look as if the universe has a center, which the universe doesn't. But carefully done, this can be a useful demonstration to use in the classroom. So that brings us towards the end here with three subtle misconceptions. They're not misconceptions in the same sense as we've been discussing here, but they're widely held beliefs and that we need to address them. So the first is the belief that somehow the positions of the sun, moon, and planets and stars influence human events and behavior. So this is something called astrology. And you've all seen your horoscopes in the paper every day. Well, scientifically, you would examine this claim by doing various experiments and studies. And dozens of studies have been done to test whether there's any evidence that astrology has an astronomical basis, and it doesn't. You can, in fact, do a very simple experiment in the classroom. You simply take yesterday's horoscopes and you cut them up and you distribute them to your students and ask them which one of those would have been appropriate for them yesterday and see whether there's any tendency for them to choose the one that corresponds to their own sun sign. But the results are always what you expect by chance. But the thing is that people who subscribe to astrology actually do seem to benefit from it. And there are reasons for that. First of all, the astrologer may be a good counselor. The horoscopes may offer good advice, so why not read all 12 of them? And if they offer good advice, then take advantage of them. And there's a very powerful effect called the placebo effect, well known in medicine, such that if you think that you are getting some kind of therapy for some disease or ailment, then you will tend to feel better. In the case of astrology, there's also this feeling of identity with your particular sign. I guess all Leos feel a certain affinity for each other and so forth. But just remember, it's not in the stars. Another widely held belief, and that is that space aliens are visiting the Earth and have visited for thousands of years. And according to Erich von Däniken, were responsible for all sorts of ancient structures like pyramids and the statues on Easter Island, blah, blah, blah. But again, there's absolutely no evidence for this, despite the fact that astronomers and many other people are studying the sky on an ongoing basis with powerful instruments and capable of recording anything that they see. But no, there is no evidence for space aliens, despite all the breathless documentaries that you will see on those particular cable channels, which I will not mention. In fact, if you believe in studies, 2% of Americans claim to have been abducted by aliens. That would be about 6 million Americans abducted by space aliens, and nobody seems to have noticed this. And finally, there's a widely held belief that the universe and the Earth and life on it were essentially created in their present form only a few thousand years ago. Now, this is based on one particular interpretation of one particular scripture, of one particular branch, of one particular religion. But it's a very powerful belief, and one that is gaining some political clout, especially in our neighbor to the south and to a little bit of an extent right here in Canada. Now, first of all, there's absolutely overwhelming evidence from all of the sciences, including astronomy, that the universe is ancient and it is evolving with time. It's billions of years old. The Earth is billions of years old. Life is billions of years old, and it has been evolving. This is something that we can trace out from the fossil record and so forth. So in this sense, there is a conflict between scientific evidence and one particular interpretation of scripture. But the important thing to go away with is that science and religion do not have to conflict. There are many scientists who have strong religious beliefs. My office mate is Muslim, and he's a practicing Muslim. I have a new colleague who's a Jesuit. I have another colleague who's an evangelical Christian, and they are all very excellent people and excellent scientists, as you can be, and if you can combine those two very important fields of endeavor. So finishing up and summarizing here, how do you get all this information that we've been discussing in the last 50 minutes or so? Well, certainly from the people that we know and respect, people who have some degree of power over us, and our community, our culture, our peers in particular. Certainly the media, increasingly the electronic media, the internet, media that are not so reputable. I won't name names here, but the best way of knowing really is finding out for yourself. Actually do the observations that I've been alluding to, do some of these simple demonstrations, do some critical thinking, and then you will be doing science. And science is fun. It's definitely something that's worth doing, and it's good for you. It's good for society, because evidence and critical thinking are more important than ever. Why? Because there's too much misinformation out there, too much fake news, as the expression goes, and it applies in society, not just to astronomy, but to much more relevant topics like the environment, health, nutrition, medicine, vaccines, climate change, and we could go on and on. And there's too much suspicion of government, and that's very often quite understood. And of science itself, maybe we don't do quite as good a job of explaining what we're doing and what the implications are. We can always do better, and that's one of the reasons why the Dunlap Institute has outreach as one of the 4 pillars of its mission. So, as I said and want to emphasize, evidence-based science and critical thinking is so important to our health, our environment, our planet, and our society. So I will end with the slide that I always end on. This is a Gary Larson cartoon. Mr. Osborne, may I be excused? My brain is full. And so we'll move on to the questions now. I'll leave this up here because my PowerPoint presentation is on that URL, the third last one there. And Neil Comans, an astronomer, has a wonderful website. It's the second last thing on this here, in which he has listed 1,500 astronomical misconceptions, and he's written a book on it called Heavenly Airs. Okay, we've got about 10 minutes for questions now, so Mike Reed is going to do his thing, and you are going to do your thing.
Okay, wonderful. Thank you very much, John, for that wonderful, wonderful talk. Generated lots of discussion in the chat. Hopefully people have had lots of their ideas challenged and maybe some misconceptions resolved if they had any. You have lots of questions. I'm going to try and make sure we get to all of them. I'm going to start with one of the most important questions first before people taper off, and that's from Mary G, who asks, if we shouldn't look at the sun, are we harming our vision when we look at the sunset or sunrise?
What was the question again?
If we shouldn't look at the sun, are we harming our vision when we look at sunset or sunrise?
Well, the sun actually appears fainter when it's close to the horizon, and that's because the sunlight gets dimmed by all of the atmosphere and pollution and dust and so forth that it passes through, and a lot of the light actually gets scattered aside. So you have to use your judgment here. If the sun really is low enough and faint enough so that you can look at it comfortably, you can take a glance at it. But you've got to realize that once it gets bright enough, particularly if you stare at it for more than a few seconds, you do run the risk of doing some damage. So I wouldn't recommend it. There are safe ways of observing the sun. If you're a teacher or anybody else, you can look these up. You can project an image with a pinhole, or you can do it in various other ways. You can do it carefully with binoculars and so forth.
Wonderful. So I think it's fair to say if you're in any doubt at all, do not look at the sun.
That's right.
Because it has serious potential to harm your vision before you even notice. Okay, lots of other questions. This one, I'm not sure if this person is quoting a specific source, but they're asking, I thought the moon was, quote, mouse brown to mouse gray.
That it was?
Mouse brown to mouse gray.
Yeah, it could be. I mean, I'm not really talking about the exact color here. We're talking about black and white movies versus color movies here. So I'll go for mouse gray or mouse brown or something like that. But its reflectivity is much closer to tar than it is to ice or snow.
So mouse gray or mouse brown to the eye, but so dark that if we measure and quantify it, it's
well, yeah. I mean,
black.
you'd actually have to go up there and look at the ground and decide what color you think it is.
Okay. So another moon question, Magnolia asks, I've heard that astronomers have been requested in court cases because people will argue that a crime was or was not visible in the moonlight. Does this actually happen?
I didn't catch that question either, the middle of it.
Sorry, Magnolia says, I've heard that astronomers have been requested in court cases because people argue that the crime either was or wasn't visible in moonlight. Does that actually happen?
So do you mean that the moonlight provided light that the crime could have occurred under?
Yeah, or I think basically, do astronomers get called to court for these kinds of things?
Well, I personally haven't been called to court, but I can well imagine, particularly in the country to the south of us, some lawyer will find some reason for bringing an astronomer in to make some particular part of the case.
Fair, okay.
What we do more often get called in is to provide evidence as to whether the sun was above the horizon, whether there was sufficient light for something to be done. This is usually in connection with car accidents.
Okay, great. So Friedel asks, what is the impact of cosmic rays on Earth?
Well, that's a complicated question. I'm not I'm not an expert on cosmic rays. I can certainly say that they're going to be much more important if you're above the atmosphere, if you're doing spacewalks, or if you're on the moon or something like that, because many cosmic rays, in fact, most of them get absorbed by the Earth's atmosphere, but there are very rare, very energetic cosmic rays which actually do get down to the level of the Earth's surface. And I'm sure that a small fraction of genetic problems could arise from something like that. In this concern, for instance, that airline pilots are getting more radiation than they would if they were working on the ground simply by flying at altitude. So there are harmful effects, less so if you're on the surface of the Earth.
Okay, thank you. So Raj asks, why is it that the longest and shortest days of the year don't occur on equinoxes?
That's because our time system is complicated by the fact that the Earth's orbit is not exactly circular, and the Earth moves slightly faster in its orbit when it's closest to the sun, and slightly slower when it's further away. And that actually causes complications as to how we define the equinoxes and so forth.
Okay, thank you. So another time question. This one says, it's from Chris P, who asks, if time is relative, how can we be certain that the Big Bang occurred approximately 14 billion years ago?
Do I have to answer that in 30 seconds?
That's what I thought. That's one where we want to have a coffee together.
This is a very sophisticated cosmological question, because you have to be allowing for the expansion of the universe. You have to be allowing for its exact properties. You have to be allowing for the light travel time and so forth. So I'm going to defer that question unless you ask me back to give another hour, but I suggest you ask a cosmologist instead.
So on that point, we do occasionally have our Ask Us Anything sessions on Cosmos from Your Couch, and those are frequently attended by cosmologists. So if you want to come back and ask that question of a genuine cosmologist, they will give you a more thorough answer. So Tom asks a related question, and again, this is another long, tricky one. Tom, I will remind you that one of the talks earlier in this series was misconceptions specifically about the Big Bang, which deals with your question a bit. But the question is, how can the universe not have a center?
Well, in the same way that the surface of a perfect sphere as a two-dimensional object does not have a center. That's the best analogy. It's not a perfect analogy. So I think I'm going to leave it at that. And also refer you to Mike Reed's first lecture in this series here, which is still archived, and listen to his misconceptions about the Big Bang.
Okay, wonderful. So a very topical question these days, do we see any evidence of Earth-like climate change on other planets?
Well, the answer is definitely yes, because global warming was in a sense discovered on Venus by a number of astronomers, including Carl Sagan. And they realized that the temperature of Venus, which is like 450 degrees Celsius, was caused by the fact that Venus's atmosphere of carbon dioxide was trapping the radiation from the sun and causing it to gradually warm up to the point that it is now, where Venus is just unbearably hot. So that really was what called attention to the greenhouse effect as an important changer of climate. So what the Earth doesn't want to do is to go the way that that Venus did. Now, equally, there is climate change on Mars, but it's rather different because Mars is further away and colder and never had nearly as much atmosphere as the Earth did. So Mars' climate has changed also very much since in the last few billion years, because we know that Mars 3 or 4 billion years ago was much more Earth-like. It had a climate that was warmer, there was more atmosphere and so forth. And so it's gone the other way. It's lost most of its atmosphere and gotten very cold.
Wonderful. So we'll just take a couple more questions. There's just a few more in the chat. We'll try and answer them all before we wrap. So the next one is again about the Big Bang. If the Big Bang has been debunked, what are your thoughts about the origin of the universe?
Well, the Big Bang has not been debunked. The evidence very strongly supports the idea that our universe emerged from a state of very high density and very high temperature, and it, along with space, expanded from this. The material and energy that was there formed into elementary particles, which then formed into atoms, molecules, and so forth. Stars formed, galaxies formed, and 13.7 billion years later, we have the universe that we know and love today. So the Big Bang is a very strongly supported theory. There are a few people who have alternate theories, but they are in the vast minority.
So I think we may have inadvertently introduced a misconception there. I think sometimes that arises when we talk about how the name Big Bang was assigned to this phenomenon by an astronomer who didn't believe in it. But still,
right.
the preponderance of astronomers do accept it.
Well, his theory was that the universe was virtually unchanged forever and ever and ever. And as the universe expanded, new galaxies formed somehow in the middle of nowhere to make up the matter in the universe. No longer.
Okay, so we have two related questions here about black holes and wormholes. One is, can you travel through a wormhole? The other is, can you travel through a black hole?
Well, if you tried to travel through the black hole that I showed you a slide of, keep in mind that the gases that were swirling into that were reaching temperatures of millions of degrees. And so you would basically be stripped into your elementary atoms and elementary particles and so forth, and you would become a plasma. And actually, the gravitational force around a black hole will do something that is very picturesquely being called spaghettification. You would be spaghettified by the tidal forces as you approach the black hole. Now, it's true that if it was a sufficiently massive black hole, the situation is slightly different, but not the kinds of black holes that we know of, because in fact, we know about them because they make material flowing into them so hot that they emit X-rays and other high energy radiation, which is not a very good thing for you.
Okay, thank you. So the very last question for tonight is maybe one of the juiciest of all, which comes from Andor Saga. And the question is, do you personally believe there are aliens in the universe?
Well, when you say believe, that really implies evidence as far as a scientist is concerned. So then you have to talk about the evidence for extraterrestrial life. Well, we know that there are hundreds of billions of stars in our galaxy, many of them with planets and many of those that are Earth-like. They're made of the same kinds of elements. They obey the same physical laws as are present here on the Earth. We know from experiments that the very simplest atoms and molecules that would have been on a planet will naturally and easily form into complex pre-biological molecules. We do not know exactly how those complex pre-biological molecules became the simplest self-reproducing things. So there is a gap in our knowledge, but I would bet that there is life elsewhere in the universe, not necessarily at our level of existence. Maybe most life is much simpler as it was on the Earth for most of the Earth's existence. But for that reason, I would be very happy if extraterrestrial life were actually discovered, even if it landed on the Earth, because it would be one of the great discoveries of all time.
Wonderful. So on that note, we will wrap for tonight. So Dr. Percy, thank you very much for dispelling so many misconceptions so quickly tonight and efficiently. I think people enjoyed the talk very, very much.
Well, I hope
For
that it
those,
was those simpler misconceptions that stuck with you. These are the ones that you are supposed to learn about in school. These are the ones that your kids or your friends are going to ask you about. The ones about black holes and big bangs and so forth, those are kind of esoteric. But there are all these everyday things that I hope you've learned a little bit about.
Thank you very much. So we're going to wrap up there, but please join us again next week, same time, for a talk about the connections between astronomy and Shakespeare. So stay safe, everybody, and we'll see you again in 1 week. Bye for now.